In this video, we're going to see how the electromagnetic waves are created. So far, we know that rate of change of electric field changes magnetic field, and rate of change of magnetic field creates electric fields. That's what we learned from the Maxwell's equation. So if you look at the Maxwell, here is the fourth equation. That's modified Amperes law. So in this modified Amperes law, d phi e by dt, rate of change of magnetic electric field, produces b magnetic field. And at the same time, Faraday's law. Faraday's law is E times n d phi by dt, where E is nothing but the voltage. Voltage we can write it as E times distance. So closed integral of E times distance. So d phi b by dt produces electric field. Okay, so that's what we learned from the previous video. So rate of change of electric field produces magnetic field. Rate of change of magnetic field produces electric field. So we'll see with a simple analogy how this is created. Now, for example, take a simple conductor, a wire with a battery. It's a DC. Okay, that's a DC source. So assume that the current is going up. So according to our right hand rule, so assume that hold that conductor in your right hand, and the thumb indicates the current direction, folding fingers indicates the magnetic field direction. So if current is going up, magnetic field here going into the board or into the screen, here it is coming out of the screen, because magnetic field is always rotating around this conductor. Okay, so here it is coming out, going in. I'm going to draw a few more dots. Okay, same thing here. Okay, now another important thing here, the electrons, when you look at the current, when the current is this is a battery, so basically this is positively charged. So this conductor, I can assume this is positively charged, this conductor is negatively charged because it is connected to the negative terminal of the battery. Okay, now we know that as long as you separate the charges, there is an electric field. So for sure here you have electric field. Okay, let me draw these dots later on. So for sure we have electric field going in this direction. Okay, so here is electric field. Okay, and here is the magnetic field. Okay, I'm going to draw on the other side too. Okay, these are the electric field lines. Starts from the positive and ends at the negative, and the magnetic field lines because of the current direction. So current is going up because of the current direction. What happens here, magnetic field is going into the screen, here coming out of the screen, going into the screen, coming out of the screen. Okay, now after some time, say I changed the direction, so now this became negative and this one became positive. Okay, again what happens, the direction is going to change. So electric field now is going to go towards up. Okay, I'm going to draw only one side. There is magnetic field and electric fields on the other side too. Okay, to avoid confusion, I'm going to just draw only one side. Now here the magnetic field direction is going to be like this. It is coming out of the board in this side. Now when I switch it, what happened to the previous field? The previous field is going to move away. So when it move away, still I have this. Here is my electric field, here is my magnetic field. This is my electric and magnetic. I just draw a couple of lines. Okay, but there are more. Now again I switch this battery direction. Now what happens? the magnetic field direction, electric field direction is going to change like to the previous first diagram. Okay. Now, what happened to these waveforms? Now these waveforms will move away. Once they move away, they're going to connect together. So how they're going to connect? So here is a simple diagram. So they're going to join together. So here I draw three lines there. Those three lines are represented right there. These three lines are represented here. So what happens there, once I switch this battery direction, second time, these waveforms and these waveforms, they're going to move away from the antenna. They're going to move away from this wire. I'm calling this as an antenna because it just look like a antenna. The technology is used in antennas basically. So these waveforms are going to combine together. Now it's a closed loop. Okay, closed loop electric field, and at the same time you'll see closed loop magnetic field. So the magnetic fields are around this, around this, around this. Okay, so there are magnetic fields. Now we know that magnetic fields carry energy, electric field they fields carry energy. That's how they store energy in the capacitor and inductor. Okay, so they can carry energy. That's how they carry energy, and they will, since they're closed loop, they can travel from one place to another place. Even they can travel through the vacuum. That's the main advantage of electric EM waves. But at the same time, these EM waves, energy in the EM waves, that energy is called radiation. Okay, here energy, I'm calling that as radiation. Okay, so that radiation is inversely proportional to the distance. Okay, so as long as the source, they're moving away from the source, they're going to lose some energy. So they're not going to, they cannot travel any further. The best example for this is your FM radio, your radio station. Those are electromagnetic waves. The radio waves are nothing but electromagnetic waves. And if you're moving away from the station like 50-60 miles, you cannot hear that because the signal is out, because these waveforms cannot travel that far from the source. That source is nothing but the antenna. Okay. And the next thing is the energy carried by this electromagnetic waves is proportional to the square of the amplitude. What is the amplitude? Let me talk about it right here. So here is the EM waves. So this red one, there. Let me take this as x-axis, y-axis, and z-axis. Okay. So the red one is the electric field, and the blue one is the magnetic field. So red one, it is traveling on the x-axis, but magnitude is changing with respect to the y-axis. And same thing, magnetic field, it is traveling in the same direction as electric field in the x direction, but the magnitude is changing with respect to the z-axis. Okay, so electric field and magnetic field lines or waves, they're perpendicular to each other. Electric waves and magnetic waves, they're perpendicular to each other when they're traveling in vacuum or air or any other means. So here the electric field is represented by, because it's sinusoidal waveform, Ey equal to E naught sine kx minus omega t, where k is 2 pi by lambda, where lambda is wavelength. Okay, and omega is angular frequency, which is 2 pi f. Okay, Ey, why I said y, because it is changing with respect to the y direction. Okay, y axis. And Bz, because magnetic field is changing with respect to the z axis. So B is equal to B naught. E naught and B naught, those are the maximum values, sine kx minus omega t. So some important points of EM waves. EM waves are transverse waves. That means they can extend over something or extend across something. Okay, now the both magnetic magnitudes of both E and B in the radiation field are found to decrease with respect to distance. As I mentioned, the magnitude of this waveform is going to decrease as it travel far away. Best example, as I mentioned, FM radio, your radio station. I mean, if you travel 50-60 miles away from the station, it's kind of hard to listen to that radio station, because that waveform does not exist anymore. Okay. um, Another important point: electric field waves and magnetic field waves are perpendicular to each other. So here is electric field, magnetic field. They are exactly 90 degrees to with each other. And next important one is electric and magnetic fields are in phase. So here they both are in phase. In phase is nothing but whenever the E is reaching the maximum value, B is also reaching the maximum value at the same time. If they both are reaching at the maximum values at the same time and zero at the same time, we call that as they're in phase. So both waveforms are in phase. Now, another important point: velocity of electromagnetic wave is, there is a big definition derivation in the textbook. I'm not going over it, but if you find it, I mean, I recommend you to go over it, but I will not ask any question in the exam. But velocity of the EM wave is 1 over square root of epsilon naught times mu naught. We indicate with c. Velocity, speed of light, we indicate with the c, which is 3 times 10 to the power of 8 meter per second. Okay, speed of, I'm saying speed of light because light is nothing but electromagnetic wave. So the energy coming from the sunlight to the earth is nothing but electromagnetic wave. Okay, so how fast that electromagnetic wave is traveling? It is traveling through the uh, outer space of the earth and vacuum. Or so the speed of light in vacuum and outer space, it's 3 times 10 to the power of 8 meter per second. But the speed of light is going to change when it is traveling through the different materials like iron or water or glass. Okay, we'll talk about it in the next chapter. But here, whenever the electromagnetic waves, whenever it is traveling through the air or vacuum, we'll take that as 3 times 10. I mean, there's a small difference, but negligible, so we'll take that as 3 times 10 to the power of 8 meter per second. Okay, it is same as current passing through the wire. Okay, actually it's not, I would say it's not current. Energy transferred in a circuit is at the speed of light. So that's the reason when we turn on the switch, immediately you see your light is turned on. But electron inside the wire travels very slow. That velocity, we call it as drift velocity. Vd equal to I over number of free electrons in that conducting material times charge of the electron and area of that conductor. Okay, so it varies based on these numbers, but that variation is very small. Basically that value will be around 10 to the power minus 4 to 10 to the power minus 5 meter per second. That's the velocity of the electron inside the conductor. That's called drift velocity. So there is a big difference how fast energy travels by using electromagnetic wave, or how fast energy travels inside the conductor by using the electrons is different than how fast the electron travels inside the conductor. Okay, c, speed of light. C has another formula, c equal to f times lambda. F is frequency in hertz, lambda is wavelength in meters. Okay, and c has another formula too, speed of light, c equal to E over B, or E naught over B naught. E naught is indicates that the amplitude or maximum value, same thing, B naught is the maximum value. So you can use RMS value or maximum value, because we know that ERMS is nothing but E naught over square root 2 for sinusoidal waveform. Okay, that's what we learned from the previous chapter. Okay, so these are the main basic important points of electromagnetic wave. Okay, the other two videos I'm going to post about electromagnetic spectrum as well as electromagnetic waves. Mm, I'm not going to make those videos, but there are some existing videos. I'm going to post them on the Blackboard. Thank you.